Have you ever noticed that some things just seem to have a speed limit? And I'm not talking about one on a sign, I mean one that's baked into the laws of physics. We're going to dive into that because it turns out there's this hidden rule for how fast things can go before they, literally start to shake themselves to pieces. And this rule, it affects pretty much everything from tiny little machines all the way up to the biggest ships on the ocean.
You know the feeling, right? Maybe it's a car that gets that weird shudder at a very specific speed on the highway. Or the classic one, a washing machine that sounds like it's preparing for takeoff during the spin cycle. That's not just random, nope. It's actually a huge clue to a really powerful idea in physics, and today we're going to figure out what is really going on. So here's our game plan. First, we'll get a handle on this hidden speed limit. Then, we'll jump into the actual science behind all that shaking. From there, we'll check out some wild examples from engineering, see how this whole concept shows up in, get this, biology. And then we'll wrap it all up by looking at how engineers cleverly design around this whole problem.
Okay, let's get to the heart of it. That wobble, that shake, it's not just a machine being old or cranky. It is a predictable physical event, and it has a name. Understanding it is the key to building pretty much anything that moves or spins.
And here it is, the big one, critical speed. So just about everything that spins has a natural rhythm, kind of like how a guitar string wants to vibrate at a certain musical note. Now, if you start spinning that object at a speed that matches that natural rhythm, well, the vibrations start to add up. They feed on each other and get bigger and bigger and bigger. That's a phenomenon called resonance, and it can be seriously destructive. Let's go right back to that washing machine. We've all been that. When the drum hits just the right RPM, its spin speed perfectly matches its natural frequency. That tiny little imbalance from your wet jeans suddenly turns into this huge violent shaking because the vibrations are just building on each other. Bam! Your washing machine has just hit its critical speed.
This right here, this is basically the golden rule of mechanical engineering. The entire game is about managing the gap between the speed you want something to run at, that's the operating speed, and the speed where it wants to tear itself apart. That's the critical speed. The whole secret to safety is to just keep those two speeds far, far away from each other.
So, let's go see how this idea plays out in the real world, shall we? We're going to look at a couple of machines that live at the extremes to see how they deal with this one single principle.
First up, let's go big, really big. This is the speed of a giant marine diesel engine, just 80 revolutions per minute. It's incredibly powerful, sure, but it's designed to run slow and steady. Why? Because that speed is intentionally way, way below its critical speed. It's all about safety and making sure that engine runs reliably for decades.
Okay, now let's jump to the total opposite end of the scale. This little component was designed to spin at a mind-boggling 80,000 RPM. But check out the test data. It failed, catastrophically, at 70,000 RPM. That was its critical speed. That was the invisible wall it couldn't get past.
So, how do you actually deal with this danger zone? Well, you've really got two main strategies. On the left, for big, heavy stuff like a cargo ship, you just stay safely below the limit, usually operating at less than 80% of that critical speed. But for super high-speed things like a jet turbine, you can't stay below. So instead, you have to accelerate so fast that you literally punch through that shaky critical speed zone before the dangerous vibrations even have time to build up.
And seriously, once you start looking, you see this principle absolutely everywhere. A saw cylinder has a set speed around 730 RPM. An industrial shaft might run between 1 and 2,000. A drone propeller screams by at 25,000 RPM. Even a high-speed train is designed in relation to its own critical velocity to make sure it doesn't start dangerously swaying on the tracks.
All right, so machines, we get it. But here's where things take a really interesting turn. It turns out that this same exact concept of operating relative to some kind of critical limit is also used by scientists to measure performance in living things.
Yeah, check this out. It's actually pretty clever. In this study, scientists first figured out each mouse's critical speed. Its personal top running speed that it can sustain. Then they based all their experiments on percentages of that number. So 80% for a nice long endurance run, 90% for high-intensity training, and then they even pushed them to 110%. That's not to be mean. That 110% test is really important. It measures their anaerobic reserve, basically how much short-burst energy they have left in the tank when they're already running at their absolute max.
And it's not just mice. It applies to human athletes too. For sprinters, coaches want to know their peak velocity, their absolute speed limit. For swimmers, they analyze performance based on a critical speed in the water to design the perfect training plan. In team sports, GPS trackers are used to see how much time a player spends in that red zone, near their personal limit, which helps coaches manage fatigue and, hopefully, prevent injuries. It's all about measuring performance against a physical threshold.
Okay, so we've seen the problem in machines, and we've seen these incredible parallels in biology. Let's bring it all home. How do engineers actually solve this problem and design things that can go super fast without shaking apart? Well, it all boils down to a pretty simple and elegant rulebook.
Here they are, the 3 big strategies. Strategy 1, stay way below. This is for things that have to be rock solid and stable, like that marine engine. Strategy 2, go way beyond it. Believe it or not, if you get far enough past the critical speed, things can actually get stable again. Some jet engines work this way. And strategy 3, if you absolutely have to cross the danger zone, you just punch through it. Hit the gas and get through it as fast as you possibly can.
So when you boil it all down, here's the key takeaway. It doesn't matter if you're designing a skyscraper, a car engine, or even an athlete's training schedule. That relationship, that gap between the operating speed and the critical speed, it's everything. It's the fundamental idea that governs safety, performance, and efficiency.
And you know, that really leaves us with a big question for the future. We want everything to be faster. Hypersonic jets, next-gen computer parts, you name it. But the laws of physics, they're not changing for us. So the real question is, how are we going to use smarter materials and more clever designs to keep engineering our way around these fundamental limits that are built into the universe?